Hi everyone. So in section 1.1 we're answering the question, what is a function? Well, functions are just a rule that takes numbers as inputs and assigns exactly one output corresponding to every input. Functions are comprised of expressions and they specify that we evaluate or how we evaluate the expression at some particular value. So for example, x squared is an expression. F of x equals x squared is now a function. That's more interesting. It's a function that's using the expression x squared essentially as its machinery for mapping values of x onto values of f of x. So for example, f of x is equal to x squared. That's one function. Now we can identify the different components of it. So we say x is the independent variable or the input. F of x is the dependent variable or the output. One way to kind of help us determine which is an independent variable and which is a dependent variable, remember the independent variable is the one that's sort of changing to influence and exert some effect upon the dependent variable. In this notation it's really easy. The f of x portion is our dependent variable. It's depending on x, which it's taking as an input. In a word problem, if you have a paragraph or something, essentially what you're going to want to look for is what is it that's changing such that it influences or exerts some influence on another variable. And whatever is acting on the other variable is probably the independent variable, and whatever is experiencing the effect is probably the dependent variable. Now this here is function notation. Alternatively, I could have written y equals x squared. You've seen that before. Here, y would be understood to be our dependent variable. And you want to be comfortable with both of these conventions for a variety of reasons. One is, well, you might have seen, or you might see in the future, in calculus, we have Leibniz and Newton conventions for writing the derivative. We don't care what the derivative is at this point. It's irrelevant for our class, but here's just a point to illustrate where we might use these different ways of referring to a function. Suppose we're using y equals x squared to refer to this function. We take the first derivative, take the derivative with respect to x, dy dx is equal to 2x. Suppose we have this version, f of x, function notation, f of x is equal to x squared. Now we take the derivative, we write f prime of x is equal to 2x. Of course these are equivalent, but we use different notation in the two cases. And depending on our application, depending on what we're trying to accomplish, one or the other might be more convenient. And you want to be able to use them interchangeably, or use our function notation and other notation interchangeably. Okay, so all functions have a domain and a range. The domain refers to the set of inputs. The range refers to the set of outputs. So here's a particular example: f of x is equal to x squared. Here's our domain, and our machinery is mapping this domain to the range. Right? Okay, sometimes we need to put restrictions on our domain. Sometimes these are intuitive, other times we have to impose them ourselves. So for example, if we have this function a of r, the area of a circle as a function of the radius, using the expression pi r squared, we know the area has to be positive, has to be non-negative, so the domain must be non-negative. Our domain within which our possible radius will live is only positive or 0, right? So non-negative values of r. And for the function a of r corresponding to the range, we're only going to allow non-negative values. Areas can't be negative. Now, of course, there's nothing mathematically wrong without putting in a negative radius here. It's going to kick out a positive area, but we have to, at this point, use our intuition and say, wait a second, there's a problem. That negative radius, we never should have entered into the function in the first place because we can't have a circle with a negative radius, right? So sometimes we have to use our own mentality to reflect on what we've done and ask if it actually makes sense, because the result of the function itself might not raise any red flags. In the case of, suppose we evaluate this at a radius of -5. Well, -5 squared is 25. That gives us an area of 25 pi. But we should all know that if we have a radius of -5, there's probably been some mistake. We're not going to try to say that it has an area of 25 pi. Okay, so let's evaluate our function. just like I was saying verbally a second ago. Let's do this now visually. So, okay, if we take a of 2, we'll plug in 2 for our radius. So pi r squared. 2 squared is 4, so we have 4 pi. The area of a circle with radius 2 is 4 pi. Or if we're going to evaluate our area of a circle for a radius of 5, we have 25 pi. And just their convenient notation is put the number first and then the Greek letter, even though this is itself a number. So the area of a circle with radius 5 is 25 pi. Okay, here's another example. Let n equals f of x be the average number of days a free agent remains in the market before being signed to a team for a contract in the millions. So we'll interpret first, f of 30 is equal to 4, and second, f of 12 is equal to 1. Well, the first one, a free agent is on the market for 30 days on average before signing for $4 million. And the interpretation of the second one is just a free agent is on the market for 12 days on average before signing for $1 million. What's the point? Well, here we see a couple things. One, function notation is giving us the ability to say something really compactly, right? So here's the short way of saying things, and here's the longer way in a sentence, right? So we can save a lot of space if we're using function notation, assuming that the person we're communicating with is able to interpret it. The other thing is that, well, we're able to say some pretty useful things about what's going on here. We can make some pretty important statements without actually knowing the underlying machinery for this function. We don't need to know its expression to make these statements. We're able to make these interpretations without knowing anything more about the function. Okay, here's another example. We have a mobile pizza delivery service with sales in dollars, S, when it sells each pie for P dollars, given this function, or is given by this function. Sales is going to be represented by the function G, which is a function of P, price. So we have 20P minus P squared. Okay, so where's the independent and dependent variables? And then let's evaluate and interpret the meaning of G of 4, G of 10, and G of 20. Okay, so for independent variables, we're looking for which variable is exerting some influence on the other. Well, when price changes, that's gonna exert an effect on sales, right? So as price rises or falls, then sales rises or falls accordingly. So price is our independent variable, and sales, or G of P, refers to our dependent variable. Okay, so G of 4 has the interpretation at a price of 4, people buy $64 worth of pizza. G of 10 had the interpretation at a price of 10, people buy $100 worth. And then note, this is our maximum actually. And then at a price of 20, people won't buy. Well, you can see that looking at this function here, right? So let's put in 20 for P. 20 times 20 is 400 minus 20 squared. 20 times 20 is 400, so this whole thing is 0. That tells us at a price of 20, S, or sales, is 0. Price is too high. Okay. Well, let's check this. Let's use our tools. Let's make a table and then use a graph. We'll think about maximizing sales, where sales is given by this function we had earlier. So here's some values for P, and here's the values that function takes on. So when price is 0, sales is 0. When price is 5, sales is $75. When price is $10, sales is $100. When price is $15, sales is $75. So our function is defined over this domain, which is going to be positive prices or non-negative prices. So it's the domain of 0 to 20, and then the range is 0 to 100. Right? And then clearly looking at the table, our maximum sales was 100 at a price of 10. And indeed, when we look at the graph, that's what's borne out, right? So here's 10, here's 100. And we see that for prices between 0 and 10, sales are rising. And then for prices between 10 and 20, sales are falling. And so there's two places where we get sales of $75. One where the price is 5 and it rises above $75 if we raise price, and the other where price is 15 and it falls below 75 if we keep raising prices, goes back up towards 100 if we lower prices. Our horizontal intercepts are where this thing crosses the price axis, so here and here, 0 and 20. And our vertical intercept, where does it cross the sales axis? Oh, only here. Okay. And the last thing is, just because there's a variable in our statement doesn't mean that just because there's a letter in our statement doesn't mean it's a variable. Letters can be a constant as well, stand for a number. So for instance, we saw pi in our area formula. That's a number. It's a constant. It doesn't vary. And by convention, since we know what pi is, we can just write in pi into our formula because it's a lot easier to stare at pi than 3.14 and then whatever it repeats to. Similarly, down here, suppose we have a rental fee of $F plus P dollars per mile, M, and this yields total price as a function of miles. So find the constants. Well, total price has to be our dependent variable, which is determined by the amount of miles. So our constants, well, P, that's our slope constant, and F, that's our intercept constant. Okay. And if you get stuck, one thing to do is think about this in terms of y equals mx plus b form. So this is like our y, this is like our plus b, this is like our m, and this is like our x, if you're thinking of y equals mx plus b form. And that'll always work. Anytime your statement is about a linear relationship, you can always think back in terms of y equals mx plus b form. That can be helpful. Okay, so here's the exercises we did. So exercise number 6, figure shows the graph of a function giving the tip t as a function of the bill b. Which of the points p, q, r in the figure tells us f of 20 is equal to 4? Okay, well, here we have b, here we have t. Here's 20, here's 4. This is what f of 20 is equal to 0. This is f of 0 is equal to 4. Here no, because this is not on the function. But this is the point 20, 0, and this is the point 0, 4. This is the point. F of 20 is equal to 4. This is the point we're after. Point R is what we're after. And then let me go, since I initially misspoke, this P, the coordinates of this point are 20, 0, right? So it goes 20 units in the horizontal direction, 0 in the vertical direction. So the coordinates of this point P are 20, 0. And then this thing goes 0 in the horizontal direction and 4 in the vertical direction. So its coordinates are 0, 0, 4. And these are not points that lie on this line. They're not points that are part of this function. But R is, right? R is on the line. R corresponds to the point where, or gives us the point where f of 20 is equal to 4. Okay, exercise 43. Suppose the price of apartments near a subway is given by price is equal to 1,000 times A divided by 10D in dollars. This looks like it's multiplied by dollars. It's not. This is just the units. We know A is the area of the apartment in square feet. D is the distance in miles from the subway. Which letters are constants and which are variables? If, suppose we want an apartment of 1,000 square feet, you want an apartment 1 mile from the subway, or you want an apartment that costs 200,000. Well, what do? Now what these are giving us, in each of these cases, they're giving us one of these letters and specifying a particular value. In other words, A, B, and C here are doing nothing other than defining constants. So this is telling us that the constant is going to be A. It's going to always take on a value of 1,000, so we can just plug in 1,000 there. So A is our constant, taking on a value of 1,000 for A. And then what is the variable? Well, it's D. It's an independent variable. Price is a dependent variable. Suppose we want an apartment 1 mile from the subway. Now this is specifying that distance is held constant at 1. So then A is our independent variable and price is our dependent variable. And then what if we have an apartment that costs 200,000? We'll plug in 200,000 over here. It's going to mean that price is held constant, and then our variables would be A and D. And then here just in the slides I've shared that logic. Okay, very good.